You know, I've been asked this question more times than I can count. At dinner parties, after lectures, in elevators, people want to know, can physics really explain where the universe came from? Can equations and experiments tell us why there's something rather than nothing? And here's the thing, it's not just casual curiosity. This question sits at the intersection of our deepest scientific understanding and our most profound philosophical and spiritual beliefs. It's a question that, it gets to the very heart of what it means to be human, right? Now, look, I'm a physicist. I spend my days thinking about strings and brains and the curvature of space-time. But this particular question, the origin of everything, well, this is where physics meets philosophy, where quantum mechanics shakes hands with theology, and where the most rigorous mathematics we have brushes up against the ultimate mystery. So let me be clear about something right off the bat. I'm not here to tell you what to believe about God. That's not what physics does. What I want to show you is something I think far more interesting. I want to show you what modern physics actually tells us about how the universe could have come into being and why that story is so astonishing that it might just change how you think about existence itself. Here's what's truly remarkable. For most of human history, the question of cosmic origins was the exclusive domain of religion and philosophy. You had creation myths, you had theological arguments, you had centuries of debate about first causes and prime movers. And physics? Well, physics was about apples falling and planets orbiting and steam engines. It had nothing to say about the ultimate beginning. But something extraordinary has happened over the past century. Physics has crashed the party, and what it's bringing to the table is not speculation, not wishful thinking, but actual mathematical frameworks, experimental observations, and testable predictions about how a universe, our universe, could emerge from what we might call nothing. Now, I know what you're thinking. Brian, come on. Something from nothing? That violates everything I learned in school. You can't get something from nothing. And you're right to be skeptical. That's the proper scientific attitude. But here's where it gets interesting. When physicists use the word nothing, we're not necessarily talking about what philosophers or theologians mean by nothing. And that distinction, that's where the real fireworks happen. Let me give you a sense of what we're going to explore together. We're going to start with what seems like a simple observation, the fact that the universe exists, and we're going to follow that thread through some of the most beautiful and bizarre ideas in modern physics. We'll encounter quantum mechanics, where particles pop in and out of existence like cosmic fireflies. We'll dive into general relativity, where gravity isn't a force but a curvature in the fabric of space-time itself. We'll explore cosmological models that suggest the universe could be self-creating, requiring no external trigger, no first mover, no divine intervention. And we'll see how all of this connects to one of the most profound questions you can ask. Why is there something rather than nothing? But before we get to the cutting edge, we need to understand how we got here. Because the story of modern cosmology, the story of how physics learned to talk about the beginning, is itself a remarkable tale of human ingenuity and courage. Let's go back about a century. In the 1920s, something astonishing happened. Astronomers using increasingly powerful telescopes began to notice something strange about distant galaxies. They were all moving away from us. Not just drifting, but speeding away, and the farther away they were, the faster they were receding. Now, this was bizarre. If you're standing in a room and you notice that everyone is moving away from you, you might think, okay, I'm at the center. But here's the remarkable thing, and this is absolutely crucial to understand. Every observer in the universe sees the exact same thing. Doesn't matter where you are, doesn't matter which galaxy you're in, you look around and everything else is moving away from you. How do you make sense of that? Well, The only way this works is if space itself is expanding. Not objects moving through space, but space itself getting bigger, stretching like the surface of a balloon being inflated. And if space is expanding now, then if you run the clock backward, everything was closer together in the past. Run it far enough back, and you arrive at something truly remarkable. A moment when all of space, all of matter, all of energy was compressed into an unimaginably small, unimaginably dense state. This is what we call the Big Bang. And let me pause here because the name is actually kind of misleading. When most people hear Big Bang, they imagine some kind of explosion in space, like a bomb going off. But that's not right. The Big Bang wasn't an explosion in space, it was an explosion of space. Space itself came into being in that moment, or at least the space we inhabit. There was no where for it to happen, and there was no before in any conventional sense. Now, you might be thinking, okay, but what caused the Big Bang? And that's a great question. It's the question, but before we can even begin to address it, we need to understand something fundamental about what physics can and cannot do. Physics is extraordinarily good at describing how things evolve, how systems change from one state to another. Give me a set of initial conditions, tell me the positions and velocities of all the particles in a system, and I can use the laws of physics to predict what happens next. That's what we do. But asking what happened before the Big Bang, well, that's like asking what's north of the North Pole. The question itself might not make sense. And here's where things get really interesting. Because modern physics, particularly quantum mechanics and general relativity, has given us ways to think about the origin of the universe that sidestep this problem entirely. They suggest that the universe might not need a cause in the traditional sense. And to understand why, we need to dive into the wonderfully weird world of quantum mechanics. You know, quantum mechanics is now about 100 years old, and I've been studying it for decades, but I still find it astonishing. At the quantum level, the realm of atoms and subatomic particles, the rules that govern our everyday world simply don't apply. And one of the most bizarre features of quantum mechanics is this. Particles can appear out of nothing. Now, let me be careful about what I mean by that. In quantum field theory, which is the framework that merges quantum mechanics with special relativity, empty space isn't really empty. It's seething with activity. The vacuum, as we call it, is filled with quantum fields, and these fields are constantly fluctuating. Energy borrowed from these fluctuations can manifest as pairs of particles, a particle and its antimatter partner that pop into existence, exist for a fleeting moment, and then annihilate back into the vacuum. These are called virtual particles, and they're not just theoretical curiosities. They have real, measurable effects. They affect the behavior of electrons in atoms. They contribute to the vacuum energy of space. They're as real as the keys in your pocket, even though they exist for just a tiny fraction of a second. Now here's the remarkable thing. The Heisenberg uncertainty principle, one of the foundational principles of quantum mechanics, tells us that there's a fundamental limit to how precisely we can know certain pairs of properties. You can't know both the exact position and exact momentum of a particle. And crucially, you can't know both the exact energy of a system and the exact time at which that energy exists. This means that for very short periods of time, quantum systems can borrow energy from the vacuum. The shorter the time, the more energy can be borrowed. And as long as everything gets paid back quickly enough, no laws are violated. So here's the audacious idea that some physicists have proposed. What if the entire universe is the ultimate quantum fluctuation? What if, instead of virtual particles popping in and out of existence, an entire universe popped into existence? Now, I know how crazy this sounds. You're probably thinking, wait a minute, Brian, the universe is huge. It has an enormous amount of energy. How could all that energy be borrowed from the quantum vacuum? And that's a brilliant objection. This is exactly where it gets beautiful. Here's the key insight, and it comes from general relativity. Gravity is weird. In fact, gravity is unique among all the forces in nature because gravitational energy is negative. Think about it this way. If you want to pull two objects apart that are gravitationally attracted to each other, say a rock and the earth, you have to add energy to the system. That means the bound state, where they're together, has less energy than the separated state. Gravitational energy is like a debt, not an asset. Now, here's where it gets wild. If you calculate the total energy of the universe, all the positive energy from matter, from radiation, from the kinetic energy of galaxies moving apart, and you add to that the negative gravitational energy from all the matter, attracting all the other matter, what do you get? Remarkably, the total comes out to be very close to zero, maybe exactly zero. This means the universe as a whole might cost nothing energetically. It's the ultimate free lunch. Let me give you an analogy. Imagine you're deeply in debt. You owe $1 million, but you also have $1 million in assets. Your net worth, zero. You started from zero, and even though you have all this activity, all this money changing hands, your total hasn't changed. The universe might be like that. Positive energy from stuff, negative energy from gravity, and the sum total is zilch. So now we can ask a different kind of question. Instead of asking, what caused the Big Bang, we can ask, given the laws of quantum mechanics and general relativity, what prevents a universe from spontaneously appearing as a quantum fluctuation if the total energy of that universe is zero? And the answer, according to some of the most brilliant physicists working today, is nothing prevents it. In fact, these laws might make it inevitable. Now, I want to be very careful here. I'm not saying that physicists have proven that the universe created itself from nothing. What I'm saying is that we have mathematical frameworks, rigorous, self-consistent theories that describe how this could happen without violating any known laws of physics. These aren't just wild speculations. They're serious scientific proposals that make predictions we can potentially test. One of the most famous of these ideas is called the Hartle-Hawking no-boundary proposal. It was developed by James Hartle and the late Stephen Hawking back in the early 1980s, and it's one of the most elegant ideas in all of physics. Here's the core insight. What if the universe doesn't have a beginning in time? What if time itself emerged along with space? Now this sounds paradoxical. How can something not have a beginning? Well, think about the surface of the Earth. If you start at the equator and head south, you eventually reach the South Pole. But what's south of the South Pole? The question doesn't make sense. There is no farther south. The South Pole is a perfectly well-defined place, but it's a boundary beyond which the concept of south loses meaning. Hartle and Hawking suggested that the Big Bang might be similar. It's not a moment in time preceded by other moments. It's the boundary of time itself. There is no before the Big Bang. In the same way, there's no south of the South Pole. To make this work mathematically, Hartle and Hawking used a brilliant trick. They took Einstein's equations of general relativity and applied them not to ordinary time, but to what's called imaginary time, a mathematical concept where the time coordinate involves the square root of -1. In this imaginary time formulation, the universe doesn't have a singular beginning point. Instead, it's smooth and well-defined everywhere, like the surface of a sphere. When you transform back to real time, what you get is a universe that emerges from a quantum state, expands and evolves according to the laws of physics. No moment of creation, no need for an external cause. The universe just is. I realize this is a lot to absorb. We're talking about imaginary time and quantum fluctuations and negative gravitational energy. But here's what I want you to take away from this first part of our journey. Modern physics has tools that can address the question of cosmic origins in ways that would have been unimaginable a century ago. We're not just speculating. We have mathematical theories grounded in our best understanding of quantum mechanics and gravity that describe how universes can come into being. Now, does this mean God doesn't exist? No, of course not. Physics can't prove or disprove the existence of God. That's not what science does. But what physics can do is show that you don't need to invoke God to explain the origin of the universe. The laws of nature might be sufficient. Whether those laws themselves require an explanation, whether they point to something deeper, well, that's a different question, and one we'll explore. But before we move on, I want to introduce you to one more idea, because it's going to be crucial for everything that follows. It's the idea of quantum cosmology, the application of quantum mechanics to the universe as a whole. And this is where things get really wild. You see, in ordinary quantum mechanics, we describe the state of a system using something called a wave function. The wave function contains all the information about the system, and it evolves according to an equation, the Schrödinger equation, that tells you how the probabilities of different outcomes change over time. Now, in the 1960s, some physicists asked a bold question: what if we write down a wave function for the entire universe, not just for particles or atoms or even galaxies, but for all of space-time itself? This is an audacious idea. It means treating the universe itself as a quantum object, subject to the same probabilistic rules that govern electrons and photons. And when you do this, when you actually write down the equations and solve them, you find something remarkable. You find that the universe can be in a superposition of different states, just like Schrödinger's famous cat can be both alive and dead, until you look. The universe can, in a sense, be in a state where it both exists and doesn't exist until some kind of observation or measurement collapses the wave function into a definite outcome. Now, I know what you're thinking. Who or what does the observing? Who collapses the wave function of the universe? And that's a profound question, one that gets at the heart of the interpretation of quantum mechanics. Some physicists argue that the wave function of the universe never collapses, that all possible histories coexist in some vast branching multiverse. Others suggest that the wave function collapses spontaneously, or that it's the act of conscious observation that does it. We don't know the answer. But what's clear is that quantum cosmology forces us to confront deep questions about the nature of reality, observation, and existence itself. Here's an analogy that might help. Imagine you're trying to understand a movie. You can describe individual frames. You can talk about how characters move from scene to scene. You can analyze the plot. But to really understand the movie, you need to think about it as a whole, the complete narrative arc, the thematic structure, the beginning and end. Quantum cosmology is like that. Instead of just describing how the universe evolves moment by moment, it tries to describe the entire history of the universe as a single, unified quantum state. And here's where the Hartle-Hawking proposal comes back in. One way to calculate the wave function of the universe is to sum over all possible histories, all possible space-time geometries that have no boundary in the past. You're essentially asking, what are all the ways the universe could have been, given that it doesn't have a beginning in the conventional sense? And when you do this calculation, you get a specific wave function that describes the most probable state of the universe. Remarkably, this wave function predicts a universe that looks a lot like ours, one that starts small and smooth, undergoes a period of rapid inflation, and then expands and cools to form the galaxies and stars we see today. Now, I need to emphasize something here. The Hartle-Hawking proposal is not the final word. It's one idea among several competing proposals in quantum cosmology. Some physicists favor a different approach called the tunneling wave function, where the universe tunnels through a quantum barrier from a state of zero size to a finite size. Others explore ideas involving string theory or loop quantum gravity. The field is very much alive, very much in flux. But what all these approaches have in common is this: they take seriously the idea that the universe can be described using the tools of quantum mechanics and general relativity, and that these tools might be sufficient to explain cosmic origins without invoking anything beyond the laws of physics. So where does this leave us? Well, let me tell you what it doesn't leave us with. It doesn't leave us with proof that the universe created itself from nothing. It doesn't leave us with a complete, tested, final theory of quantum gravity. And it certainly doesn't leave us with a definitive answer to whether God exists. What it does leave us with is something profound and humbling. The recognition that the laws of nature are far stranger, far more subtle, and far more powerful than we ever imagined. When I think about the quantum vacuum, seething with virtual particles, I'm astonished. When I think about space-time itself as a dynamical entity that can flex and curve and even come into being, I'm humbled. When I think about the possibility that the universe's total energy is zero, that existence itself is a kind of cosmic accounting trick, I feel a sense of wonder that no amount of scientific training can diminish. But here's the thing. The question we started with, can physics explain the origin of the universe without God? That question rests on some assumptions that we need to examine more carefully. What do we mean by explain? What do we mean by without God? And most importantly, what do we mean by nothing? You see, when physicists talk about a quantum vacuum, we're talking about a state with very specific properties. It has quantum fields, it obeys the laws of quantum mechanics, it has energy fluctuations. Is that really nothing? Or is it just a very subtle, very strange kind of something? And if it is something, then where did it come from? Where did the laws of quantum mechanics come from? Where did space-time itself come from? These are not idle questions. They're questions that philosophers and theologians have been asking for centuries, and they're questions that some physicists, myself included, find ourselves grappling with more and more as our understanding deepens. Because here's what I've come to appreciate. The more we learn about the universe, the more we realize how much we don't know. Every answer opens up new questions. Every mystery we solve reveals deeper mysteries. Let me give you a concrete example. We know that the universe has certain properties, the strength of gravity, the mass of the electron, the speed of light that seem remarkably fine-tuned for the existence of complex structures like galaxies, stars, and ultimately life. Change any of these values by even a small amount, and you get a universe where stars can't form, where atoms don't exist, where life as we know it is impossible. Now, why should the universe have these particular values? One answer is pure chance. We got lucky. Another answer is that there's an infinite multiverse, and we live in one of the universes where the parameters happen to be right for life. A third answer is that some deeper principle, some yet-to-be-discovered law, determines these values necessarily. And a fourth answer, of course, is that they were chosen by a conscious designer for the purpose of creating life. Physics can explore the first three possibilities. We can develop theories that predict multiverse scenarios. We can search for deeper principles that constrain the constants of nature. But the fourth possibility, designed by a conscious agent that's beyond the scope of physics as currently practiced, not because it's wrong, but because it's not a question physics knows how to address with experiments and observations. And this brings us to a crucial point. When we ask, can physics explain the origin of the universe without God, we're really asking two different questions. One is a technical question about whether the laws of physics as we understand them are sufficient to account for cosmic origins. And the answer, I think, is fascinating. Maybe yes. The framework exists. The mathematics works. We have models that are self-consistent and that don't require any external input. But there's a deeper question lurking underneath. Where do the laws of physics themselves come from? Why do we have quantum mechanics and not some other set of rules? Why is there something rather than nothing, not just in terms of matter and energy, but in terms of laws, principles, mathematical structures? And this question, this deeper why, that's not a question physics answers. It might not even be a question physics can answer. You know, Richard Feynman, one of the greatest physicists of the 20th century, once said, "Physics is like sex. Sure, it may give some practical results, but that's not why we do it." What he meant was that the real joy of physics is not in the applications or even in the answers. It's in the questions themselves. It's in the process of pushing the boundaries of human understanding, of confronting mystery with mathematics, of seeing patterns where others see chaos. And the origin of the universe? This is the ultimate question. It's the place where physics meets philosophy, where science meets spirituality, where our most sophisticated mathematical tools brush against the ineffable. And what I find so beautiful about this moment in history is that for the first time ever, we have real, substantive things to say about it. Not final answers, but real progress. Let me paint a picture for you of where we are. Imagine humanity's understanding of cosmic origins as a vast, dark room. For most of our history, we've been stumbling around in that darkness, lighting occasional matches, creation myths, philosophical arguments, theological doctrines that give us fleeting glimpses of our surroundings. But in the past century, we found the light switch. And what we're seeing is astonishing. We're seeing that the universe has a history that we can trace back billions of years. We're seeing that the laws governing this history are mathematical and precise. We're seeing that these laws might be sufficient to explain how the universe came into being without invoking anything supernatural. And we're seeing that the deeper we look, the stranger and more wonderful it all becomes. But here's what's crucial. Turning on the light doesn't mean we understand everything we see. In fact, it reveals just how much more there is to understand. The room is bigger than we thought. There are doors we didn't know existed. And beyond those doors, more questions, more mysteries, more astonishing possibilities. So when I'm asked, can physics explain the origin of the universe without God? My answer is this. Physics can show that the origin of the universe doesn't require supernatural intervention in any obvious way. The laws of nature, as we understand them, seem capable of bringing about a universe without external input. But those laws themselves, their existence, their particular form, their capacity to give rise to a universe like ours, that's a deeper question. And whether you call the answer to that deeper question God or the mathematical structure of reality or something else entirely, well, that depends on your philosophical and spiritual commitments, not on what physics can tell you. What I can tell you is this. We're living in an extraordinary time. For the first time in human history, we have serious scientific theories about how the universe began. We have equations that describe the first fraction of a second after the Big Bang. We have frameworks for thinking about what before the Big Bang might even mean. And we have observational tests, measurements of the cosmic microwave background, observations of distant supernovae, studies of gravitational waves that are beginning to constrain and test these ideas. And here's the truly exciting part. We're nowhere near done. The field of quantum cosmology is still young. Our theories of quantum gravity are incomplete. We're still learning how to make sense of the quantum nature of space-time. Every year brings new insights, new observations, new theoretical developments. The story of cosmic origins is still being written, and the most astonishing chapters might still lie ahead. I want to close this first part with a thought. You know, there's a tendency to see science and religion as competitors, as two different teams fighting for the same territory. And certainly, there are areas where specific scientific claims conflict with specific religious doctrines. But at the deepest level, I think this framing misses something important. Science and religion are asking different kinds of questions. Science asks how things work. What are the laws? What are the mechanisms? How can we predict what will happen next? Religion asks why things are. What is the purpose? What is the meaning? How should we live? These questions touch, they overlap, they inform each other, but they're not identical. When physics proposes that the universe could emerge from a quantum fluctuation without external cause, it's answering a how question. It's saying, here's a mechanism that doesn't violate any known laws, but it doesn't answer the why questions. Why are there laws at all? Why does mathematics describe reality? Why does anything exist? These are questions that science touches but cannot fully resolve. And you know what? I think that's okay. I think it's more than okay. I think it's wonderful because it means there's room for wonder, room for mystery, room for different ways of knowing and different frameworks for understanding. The fact that physics can describe a self-creating universe doesn't diminish the awe I feel when I contemplate existence. If anything, it deepens it. Because here's what quantum cosmology is really telling us. The universe is far stranger than we ever imagined. It's not just strange in its details, quantum entanglement, black holes, dark energy. It's strange in its very existence. The boundary between being and non-being, between something and nothing, between existence and the void, these boundaries are not sharp, they're quantum. They're fuzzy. They're subject to probabilities and superpositions and all the weirdness that makes quantum mechanics so fascinating and so frustrating. So as we move forward, as we dive deeper into these ideas, I want you to hold on to that sense of strangeness. Don't let the equations and the technical jargon fool you into thinking we've got it all figured out. We don't. We're explorers, mapping out new territory, and the map is full of blank spaces marked, "Here be dragons." But those dragons, they're not threats. They're invitations. They're calling us to look closer, to think harder, to imagine more boldly. And in the next part of our journey, we're going to answer that call. We're going to explore what nothing really means in physics. We're going to look at how quantum mechanics and general relativity combine to create the possibility of spontaneous universe creation. We're going to meet some of the key players in this scientific drama, from Alan Guth's inflationary universe, to Stephen Hawking's imaginary time, to Lawrence Krauss's universe from nothing. And we're going to confront head-on the philosophical objections, the theological concerns, and the conceptual puzzles that these ideas raise. Because this isn't just about physics. This is about what it means to exist, what it means to understand, and what it means to ask the biggest questions we can ask. The universe had a beginning, or did it? It emerged from nothing, or did it emerge from something we don't yet fully understand? The laws of physics explain everything, or do they just push the mystery back one level? These are the questions that keep me up at night. These are the questions that make physics not just a profession, but a calling. Now, before we move to the next part, I want to spend a little more time on something that's absolutely foundational to everything we're discussing, the quantum vacuum. Because when physicists say the universe could emerge from nothing, what we really mean is that it could emerge from the quantum vacuum. And understanding what that is, really understanding it, is crucial. So let's talk about what empty space actually is. In your everyday experience, empty means, well, empty. No stuff. If I take a box and pump out all the air, all the molecules, every last atom, I've got empty space, right? That's what Newton would have said. That's what common sense says. But quantum mechanics tells us something profoundly different. It tells us that you can never truly empty that box. You can remove all the particles, sure, but you can't remove the fields. What's a field? Well, think about the electromagnetic field. It's what allows charged particles to interact with each other. It's what carries light from the sun to your eyes. Even when there are no particles present, the field is still there, pervading all of space. And according to quantum mechanics, this field is never completely still. It's always fluctuating, always jittering. Even in its lowest energy state, the ground state, the vacuum state, These fluctuations are not optional. They're required by the Heisenberg uncertainty principle. You cannot have a quantum field that sits perfectly still at zero energy, because that would mean you know both its value and its rate of change with perfect precision, which quantum mechanics forbids. The field must fluctuate. And these fluctuations can briefly manifest as pairs of particles, what we call virtual particles. Let me give you a concrete example. In the vacuum around us, right now, electron-positron pairs are constantly popping into existence. An electron, negatively charged, and a positron, its antimatter partner, positively charged, appear, exist for a tiny fraction of a second, and then annihilate back into the vacuum. They never live long enough to be directly detected, but their effects are real and measurable. They alter the energy levels of electrons in atoms by a tiny amount, an effect called the Lamb shift, which has been measured to extraordinary precision and matches the predictions of quantum field theory perfectly. So when we talk about the universe emerging from nothing, we're talking about it emerging from this quantum vacuum, a state where there are no particles, but where quantum fields exist and fluctuate. Now, you might say, but Brian, that's not nothing. That's something. And you're right. That's exactly the point that philosophers like David Albert make. The quantum vacuum has structure, has laws, has properties. It's not the philosopher's nothing, the absolute absence of anything. It's the physicist's nothing, the lowest energy state of fields that pervade space-time. But here's the remarkable thing. Even this physicist's nothing might not be the deepest level, because the quantum fields themselves exist in space-time, and space-time is also a dynamical entity according to general relativity. So we can ask, could space-time itself emerge from an even deeper nothing? Could the quantum fields themselves emerge? And this is where we need quantum gravity, a theory that treats not just matter and energy quantum mechanically, but space and time themselves. And here's where it gets truly wild. In quantum gravity, space-time isn't this fixed stage on which events play out. It's part of the quantum show. It can be in superpositions, it can fluctuate, and at the Planck scale, about 10 to the power of minus 35 meters, far smaller than an atom, space-time itself becomes grainy, foamy, uncertain. The very notion of a smooth geometric space breaks down. Some physicists, like Lawrence Krauss, argue that this is as close to true nothing as we can get, a state where even space-time hasn't yet taken form, where only the abstract laws of quantum gravity exist. And from this state, universes can spontaneously nucleate like bubbles forming in boiling water. The laws allow it, the mathematics describes it, and nothing prevents it. But now we're back to that deeper question. Where do the laws come from? If universes can emerge from nothing, but that nothing obeys quantum mechanical laws, then those laws themselves are something. They're not physical entities, not particles or fields or space-time geometries. They're abstract mathematical structures. But they're something nonetheless. So, have we really explained creation from nothing? Or have we just pushed the question back to why these laws and not others? This is not a question physics can answer, at least not physics as currently practiced. We can discover what the laws are, we can test them, refine them, unify them. But asking why those particular laws exist rather than others, that's what philosophers call a metaphysical question. It's beyond the reach of experimental verification. Now, some physicists are comfortable with that. They say, look, the laws just are. They're brute facts about reality, and there's nothing deeper to explain. Others think there might be a deeper level, a theory of everything, that not only unifies all the forces, but explains why the universe must have the particular laws it does. Maybe there's only one mathematically consistent way for a universe to exist, and we're gradually discovering what that is. Maybe, as Stephen Hawking once suggested, the universe exists simply because it would be mathematically inconsistent for it not to exist. But let me be honest with you. These are speculations. Beautiful, intriguing speculations, but speculations nonetheless. We don't have a theory of everything. We don't have a complete theory of quantum gravity. And we certainly don't have a mathematical proof that the laws of physics are the only logically possible laws. What we do have is something remarkable enough. We have frameworks that show how the universe could begin without violating physical law. We have theories that are mathematically consistent and that make predictions we can test. And we have a growing recognition that the origin of the universe is not forever beyond the reach of science. Let me tell you about one more idea that's going to be important as we move forward: cosmic inflation. In the early 1980s, a physicist named Alan Guth proposed a remarkable solution to some puzzles about the Big Bang. He suggested that in the first tiny fraction of a second after the universe began, it underwent a period of exponentially rapid expansion, expanding by a factor of at least 10 to the power of 26 inches, less than 10 to the power of minus 32 seconds. This sounds crazy, I know. But inflation solves several problems. It explains why the universe is so uniform on large scales, because regions that are now separated by billions of light years were once close enough to reach thermal equilibrium before inflation blew them apart. It explains why the universe is so flat, because inflation stretches out any initial curvature, like blowing up a balloon until its surface looks flat. And it explains the origin of the tiny fluctuations we see in the cosmic microwave background, because quantum fluctuations during inflation get stretched to cosmic scales and frozen in as density variations that eventually become galaxies. But here's what's really interesting for our discussion. During inflation, the energy driving the expansion comes from what's called an inflaton field, a hypothetical quantum field that exists in a high energy state. As the universe expands, this field slowly rolls down to a lower energy state, and when it reaches the bottom, the energy gets converted into particles and radiation, the hot Big Bang. So inflation provides a mechanism for converting the vacuum energy of a quantum field into the matter and energy we see around us. And here's the kicker: in some versions of inflation, particularly eternal inflation, the process never fully stops. In most regions, the inflaton field reaches its minimum and inflation ends, creating a pocket universe like ours. But in other regions, quantum fluctuations can boost the field back up, causing inflation to continue. This creates a vast multiverse, an infinite collection of pocket universes, each potentially with different properties, different laws, different values for the fundamental constants. Now, why am I telling you this? Because the multiverse has profound implications for the question of cosmic origins. If there's a multiverse, and if different pocket universes can have different properties, then the fact that our universe seems fine-tuned for life is no longer surprising. We exist in one of the universes where the conditions happen to be right. The vast majority of universes might be sterile, lifeless, but we wouldn't be around to observe those. We're necessarily in a universe capable of supporting observers, a principle called the anthropic principle. This is hugely controversial. Some physicists love the multiverse because it solves the fine-tuning problem elegantly. Others hate it because it seems to give up on the goal of explaining why our universe has the particular properties it does. If anything goes somewhere in the multiverse, then our theories lose predictive power. We can't say the electron must have this mass because of this deep principle. We can only say in our universe the electron happens to have this mass. But here's what I find fascinating. Whether you like the multiverse or not, it emerges naturally from our best theories of inflation and quantum mechanics. We didn't invent it to solve philosophical problems. We discovered it, or at least found it to be a generic consequence of ideas we developed for completely different reasons. And that's often how physics works. You're studying one thing, and something else, something unexpected and profound, falls out of the equations. So let me pull together where we've been. We've seen that the universe appears to have had a beginning about 13.6 0.8 billion years ago. We've seen that quantum mechanics allows particles and potentially entire universes to appear spontaneously from vacuum fluctuations. We've seen that the total energy of the universe might be zero, making such a spontaneous appearance energetically free. We've seen proposals like the Hartle-Hawking no-boundary condition that describe the universe's quantum state without invoking an external cause. And we've seen how inflation could generate a vast multiverse of pocket universes with varying properties. All of this adds up to a remarkable conclusion. The laws of physics, as we currently understand them, are capable of accounting for the origin and evolution of the universe without requiring anything beyond those laws. No supernatural intervention, no first cause, no unmoved mover, just quantum mechanics, general relativity, and the fields and particles they describe. But, and this is crucial, this doesn't mean we've explained everything. We haven't explained why there are laws at all. We haven't explained why mathematics works so unreasonably well in describing the physical world. We haven't explained consciousness or meaning, or why the universe contains these particular structures rather than others. And we certainly haven't explained why there's something rather than nothing at the deepest possible level. What we've done is show that you can have a universe without a divine creator if you grant the existence of physical laws and quantum fields. But those laws and fields are themselves something. They have structure, they have properties, they have causal power. So in a sense, we've translated the question, why is there something rather than nothing, into why are there laws of physics? And that's progress. It's real progress, but it's not a final answer. You know, Einstein famously said, the most incomprehensible thing about the universe is that it is comprehensible. What he meant was that it's astonishing that we evolved primates on a small planet can understand the deep structure of reality using mathematics and experiments. There's no obvious reason why the universe should be intelligible to us, and yet it is. This intelligibility is itself a kind of mystery. The laws of physics are elegant, mathematical, universal. They hold at the edge of the observable universe just as they hold in this room. They held a microsecond after the Big Bang, and they'll hold trillions of years in the future. Why? Why should the universe be governed by laws at all, let alone laws with such beauty and economy? Some people see in this an argument for design. The laws are fine-tuned, elegant, and life-permitting. Surely that points to a cosmic designer. Others see in it simply a brute fact, or perhaps a consequence of deeper mathematical necessity. And still others see in it an invitation to further scientific inquiry. Maybe we'll discover a deeper level of explanation that tells us why the laws must be as they are. I don't know the answer. I don't think anyone does. But what I do know is that the question itself is profound, and that grappling with it using the tools of physics, philosophy, and theology is one of the great intellectual adventures of our time. Let me share with you one more thought experiment before we wrap up this first part. Imagine that you're trying to explain to someone from the 18th century, say Thomas Jefferson or Immanuel Kant, what modern physics has discovered about cosmic origins. How would you even begin? You'd have to explain relativity, that space and time are interwoven, that gravity is curvature, that the speed of light is absolute. You'd have to explain quantum mechanics, that particles are waves, that outcomes are probabilistic, that measurement affects reality. You'd have to explain the expansion of the universe, the Big Bang, the cosmic microwave background, and then you'd have to explain that we can write down equations describing the quantum state of the entire universe, including its origin. Your 18th century interlocutor would think you were insane, or a mystic, or both. Because what you're describing is so far removed from everyday experience, so contrary to intuition, that it sounds like mythology or metaphysics rather than science. And yet, it's science. It's based on observations, experiments, mathematical rigor. We've seen the evidence for expansion.
The question of origin, whether science can explain the beginning of the universe without invoking the idea of God, is one of the most profound and enduring questions in human history. It sits at the intersection of physics, philosophy, and theology, and challenges the limits of human understanding. When we ask how the universe began, we are not just asking a scientific question. We are also asking about meaning, purpose, and existence itself. From a scientific perspective, the effort to understand the origin of the universe is rooted in observation, experimentation, and mathematical modeling. Modern cosmology, built upon the work of great thinkers like Albert Einstein, has given us a framework to describe how the universe behaves on the largest scales. Einstein's theory of general relativity revealed that space and time are not fixed backgrounds, but dynamic entities that can expand, contract, and curve. This discovery opened the door to the idea that the universe itself could have a beginning. Observational evidence further strengthened this view. In the early 20th century, Edwin Hubble discovered that distant galaxies are moving away from us, indicating that the universe is expanding. This observation led scientists to conclude that if we trace this expansion backward in time, everything must have once been concentrated in an extremely dense and hot state. This idea is known as the Big Bang Theory, which is currently the leading scientific explanation for the beginning of the universe. The Big Bang model does not describe an explosion in space, but rather an expansion of space itself. It suggests that space, time, matter, and energy all came into existence at a finite point in the past, approximately 13.8 billion years ago. This is a remarkable conclusion because it implies that the universe has not existed forever. Instead, it had a beginning, a moment when everything we know came into being. At first glance, this scientific explanation might seem to eliminate the need for any supernatural cause. If science can explain how the universe began, why would we need to invoke God? However, this is where the question becomes more complex. Science is incredibly powerful at describing how things happen, but it is less equipped to answer why they happen. The Big Bang Theory explains the evolution of the universe from its earliest moments, but it does not fully explain why the Big Bang occurred in the first place. This leads us to a deeper philosophical issue: the difference between scientific explanation and ultimate explanation. Scientific explanations are based on laws of nature rules that describe how matter and energy behave. But these laws themselves raise questions. Where did the laws of physics come from? Why do they exist at all? Why do they have the specific form that allows a universe like ours to exist? These are questions that science can approach, but may not be able to answer definitively. Some scientists have proposed that the universe could have arisen spontaneously from a quantum vacuum. In quantum mechanics, what we think of as empty space is not truly empty. It is filled with energy and fluctuations that can give rise to particles. According to this idea, the universe could have emerged from a quantum fluctuation without the need for an external cause. This concept suggests that the universe could, in some sense, create itself. However, this idea introduces another layer of complexity. The quantum vacuum is not nothing. It is a physical system governed by laws of quantum physics. If the universe came from such a state, we are still left with the question of why that state exists, and why the laws governing it are the way they are. In other words, even if science can describe a mechanism for the origin of the universe, it does not necessarily eliminate the need for a deeper explanation. This is where the concept of God often enters the discussion. In many religious traditions, God is seen as the ultimate cause of the universe, the reason why there is something rather than nothing. From this perspective, science and religion are not necessarily in conflict, but address different aspects of the same question. Science explains the processes and mechanisms of the universe, while religion addresses questions of purpose, meaning, and ultimate origin. Philosophers have long debated whether the existence of the universe requires a cause beyond itself. One argument suggests that everything that begins to exist must have a cause. Since the universe began to exist, it must have a cause. Some interpret this cause as God. Others argue that the universe could be self-contained, with no need for an external cause. The debate continues with no clear consensus. Another important consideration is the limitation of human understanding. Our minds are shaped by everyday experiences within space and time. When we try to think about the beginning of the universe, when space and time themselves came into existence, we are venturing beyond the limits of our intuition. Concepts like before the Big Bang or nothingness may not even make sense in the way we normally understand them. This makes the question of origin especially difficult to answer. In recent years, some scientists have explored ideas such as the multiverse, which suggests that our universe may be just one of many. In such models, universes could be constantly forming, each with different physical laws. If this is true, the origin of our universe might be explained as part of a larger, self-sustaining system. However, the multiverse itself raises the same fundamental question: why does this larger system exist? Ultimately, the question of whether science can explain the beginning of the universe without God remains open. Science has made incredible progress in describing the early universe and uncovering the laws that govern it. It has given us a detailed picture of how the universe evolved from its earliest moments to the present day. Yet, the deepest questions why there is something rather than nothing, and why the laws of nature exist, may lie beyond the reach of scientific inquiry. This does not mean that science has failed. Rather, it highlights the boundaries of what science can do. Science is a tool for understanding the natural world, based on observation and evidence. It is not designed to answer every possible question, especially those that involve meaning, purpose, or ultimate causes. These questions may require philosophical or theological perspectives alongside scientific ones. In the end, the question of origin invites us to explore both the power and the limits of human knowledge. It challenges us to think deeply about the nature of reality and our place within it. Whether one believes that science alone can explain the universe or that a higher power is necessary, the search for answers continues to inspire curiosity, wonder, and a sense of awe about the universe we inhabit. The idea that the universe had a beginning is one of the most revolutionary concepts in modern science. For much of human history, people believed that the universe was eternal and unchanging. Philosophers and scientists alike assumed that the cosmos had always existed in roughly the same form. However, this view began to change dramatically in the 20th century, when scientific discoveries revealed that the universe is dynamic, evolving, and expanding. This led to the development of one of the most important ideas in cosmology, the Big Bang theory. The Big Bang theory proposes that the universe began approximately 13.8 billion years ago from an extremely hot, dense state. It was not an explosion in space, but rather an expansion of space itself. At that initial moment, all matter, energy, space, and even time were compressed into a single point of immense density. Then, in a fraction of a second, the universe began to expand rapidly, and it has continued expanding ever since. This theory fundamentally changed our understanding of the cosmos, suggesting that the universe has a finite age and a definite beginning. One of the key reasons scientists accept the Big Bang theory is because it is supported by strong observational evidence. One of the most important pieces of evidence comes from the work of Edwin Hubble. In the 1920s, Hubble observed distant galaxies and discovered that they are moving away from us. Even more importantly, he found that the farther away a galaxy is, the faster it appears to be receding. This observation led to the conclusion that the universe is expanding in all directions. If the universe is expanding today, then logically, it must have been smaller in the past. By reversing this expansion in our calculations, scientists realized that there must have been a time when everything in the universe was concentrated into an incredibly small and dense state. This idea provided the first major support for the concept of a cosmic beginning. The expansion of the universe is not just a theory. It is directly observed through the redshift of light from distant galaxies, making it one of the most solid pieces of evidence in cosmology. Another powerful piece of evidence for the Big Bang comes from the discovery of the cosmic microwave background radiation. In 1965, two scientists, Arno Penzias and Robert Wilson, accidentally discovered a faint microwave signal coming from all directions in space. This radiation is essentially the afterglow of the early universe, a remnant of the time when the universe was hot and dense. As the universe expanded and cooled, this radiation spread out and can still be detected today. The cosmic microwave background is incredibly uniform, but it contains tiny fluctuations that provide important clues about the early universe. These small variations in temperature represent the seeds of all the structure we see today: galaxies, stars, and clusters of matter. The existence of this radiation strongly supports the idea that the universe was once in a hot, dense state, exactly as predicted by the Big Bang theory. In addition to expansion and background radiation, another line of evidence comes from the abundance of light elements in the universe. According to the Big Bang model, the early universe was so hot that nuclear reactions occurred within the first few minutes, forming simple elements such as hydrogen, helium, and small amounts of lithium. Observations of the universe today show that these elements exist in exactly the proportions predicted by the theory. This remarkable agreement between prediction and observation further strengthens the case for the Big Bang. While the Big Bang theory provides a detailed explanation of how the universe evolved after its beginning, it also raises deeper questions about the nature of that beginning. What exactly happened at the moment of the Big Bang? What caused it? And what, if anything, existed before it? These questions push the limits of scientific understanding. One of the challenges in studying the beginning of the universe is that the laws of physics, as we currently understand them, break down under extreme conditions. As we approach the very beginning, often referred to as the singularity, our equations no longer provide reliable answers. This is because general relativity, the theory developed by Albert Einstein, does not fully account for quantum effects, which become extremely important at such small scales. To truly understand the origin of the universe, scientists are working to develop a theory of quantum gravity, which would combine general relativity with quantum mechanics. Such a theory could potentially explain what happened at the very beginning and whether the Big Bang was truly the start of everything or just a transition from an earlier state. However, this remains one of the greatest challenges in modern physics. Some theories suggest that the Big Bang may not have been the absolute beginning. For example, certain models propose that the universe could have gone through cycles of expansion and contraction, or that it emerged from a pre-existing quantum state. Others suggest that our universe may be part of a larger multiverse, where new universes are constantly being created. These ideas are still highly speculative, and there is currently no direct evidence to confirm them. Despite these uncertainties, the Big Bang theory remains the best scientific explanation we have for the origin of the universe. It is supported by multiple independent lines of evidence, including the expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements. These observations all point to the same conclusion. The universe had a beginning, and it has been evolving ever since. However, it is important to recognize that the Big Bang theory does not answer every question. It describes how the universe developed from its earliest moments, but it does not fully explain why the universe exists in the first place. This distinction is crucial. Science excels at explaining processes and mechanisms, but questions about ultimate causes and purpose often extend beyond the scope of scientific inquiry. The evidence for a beginning of the universe has profound implications, not only for science, but also for philosophy and religion. The idea that the universe had a starting point raises questions about what, if anything, caused it to begin. Some see this as pointing toward a deeper explanation beyond science, while others believe that future scientific discoveries will provide the answers. In conclusion, the Big Bang theory represents one of the greatest achievements of modern science. It provides a coherent and evidence-based explanation for the origin and evolution of the universe. Through observations of cosmic expansion, background radiation, and elemental abundances, scientists have built a compelling case for a universe that began in a hot, dense state billions of years ago. Yet, even with all this knowledge, the ultimate origin of the universe remains a mystery, reminding us that the search for understanding is far from complete. The laws of physics and the concept of quantum fluctuations play a central role in modern scientific attempts to explain the origin of the universe without invoking a divine cause. This keynote explores a profound and often misunderstood idea, that the universe might have emerged naturally from physical laws themselves. It challenges our intuitive understanding of nothingness and asks whether the universe could arise spontaneously, governed only by the principles of physics. To understand this idea, we must first consider what scientists mean by the laws of physics. These laws are mathematical descriptions of how the universe behaves. They explain how matter moves, how forces interact, and how energy is transferred. From the motion of planets to the behavior of subatomic particles, everything in the universe appears to follow these consistent rules. These laws are not just human inventions. They are discovered through observation and experiment, revealing patterns that exist in nature itself. One of the most important developments in physics came from the work of Isaac Newton, who described the laws of motion and gravity, showing that the same principles that govern falling objects on Earth also apply to the movement of planets in space. Later, Albert Einstein revolutionized our understanding of space and time, demonstrating that gravity is not a force in the traditional sense, but a curvature of spacetime. These discoveries revealed that the universe operates according to deep and elegant mathematical principles. However, when scientists began studying the smallest scales of reality, they discovered that the classical laws of physics were not sufficient. At the level of atoms and subatomic particles, the universe behaves in ways that seem strange and counterintuitive. This led to the development of quantum mechanics, a branch of physics that describes the behavior of particles at extremely small scales. Quantum mechanics introduced a radical idea that the universe is fundamentally probabilistic rather than deterministic. Instead of exact outcomes, it deals with probabilities. One of the most surprising features of quantum physics is the concept of fluctuations in what appears to be empty space. In everyday life, we think of a vacuum as completely empty, but in quantum physics, even the emptiest space is filled with activity. According to quantum theory, particles and antiparticles can spontaneously appear and disappear in extremely short periods of time. These are known as quantum fluctuations. They occur because of the uncertainty principle, first described by Werner Heisenberg, which states that certain pairs of physical properties, such as energy and time, cannot both be precisely determined. As a result, small amounts of energy can briefly appear out of nowhere, giving rise to temporary particles. This idea has led some scientists to propose that the entire universe could have originated from a quantum fluctuation. In this view, the universe did not need a cause in the traditional sense. Instead, it could have arisen naturally from the laws of quantum physics. The universe, in this sense, is not something that was created from nothing, but something that emerged from a quantum vacuum, a state governed by physical laws. One of the most well-known proponents of this idea was Stephen Hawking, who argued that because there are laws such as gravity, the universe can and will create itself from nothing. This statement is often misunderstood. Hawking did not mean nothing in the philosophical sense of absolute non-existence. Rather, he referred to a quantum state where the laws of physics still apply, even if there is no classical matter or space as we understand it. Another physicist, Lawrence Krauss, has also argued that the universe could arise from a quantum vacuum. He suggests that the laws of physics allow for the spontaneous creation of universes, much like quantum particles appear and disappear. In this framework, the existence of the universe does not require a supernatural explanation. It is a natural consequence of the underlying physical laws. However, this explanation raises important philosophical questions. If the universe can arise from a quantum vacuum, where did that vacuum come from? Why do the laws of physics exist at all? The quantum vacuum is not truly nothing. It is a complex structure governed by mathematical rules. So even if the universe can emerge from such a state, we are still left with the question of why that state exists. This leads to a deeper issue. Can laws of physics exist independently of the universe? Some scientists argue that the laws of physics are fundamental. They simply exist as part of reality. Others suggest that the laws themselves might be emergent, arising from deeper principles that we do not yet understand. In either case, the existence of these laws is not fully explained by current science. Another challenge is that quantum mechanics, while incredibly successful, is not yet fully unified with general relativity. General relativity describes the large-scale structure of the universe, while quantum mechanics describes the smallest scales. At the moment of the universe's origin, both of these theories would be important, but they do not yet fit together into a single, complete theory. Scientists are working on developing a theory of quantum gravity to bridge this gap, but it remains an open problem. Despite these challenges, the idea that the universe could arise from quantum fluctuations is a powerful one. It shows that the laws of physics may be capable of explaining phenomena that were once thought to require supernatural explanations. It also highlights the remarkable ability of science to push the boundaries of human knowledge, exploring questions that were once considered beyond reach. At the same time, this idea does not necessarily eliminate the concept of God. Some people interpret the laws of physics themselves as evidence of a deeper order or design. Others see them as self-contained, requiring no external explanation. The question ultimately depends on how one interprets the relationship between science and philosophy. In conclusion, the laws of physics and quantum fluctuations offer a fascinating perspective on the origin of the universe. They suggest that the universe may have arisen naturally from a quantum state, governed by fundamental principles of physics. This challenges traditional ideas about creation and causality, showing that the universe might not require an external cause in the way we usually think. However, it also raises deeper questions about the origin of the laws themselves and the nature of reality. While science provides powerful tools for understanding the universe, it may not yet have all the answers, leaving room for ongoing exploration, debate, and wonder.